the second part of Chapter 2 of this course, we're going to turn to looking at relations, the generalization of the idea of functions. Before we do that, let's have a look again at how we could define a function. Recall that if you've got two sets A and B, a function, f from A to B, it's a rule that takes each element of A to exactly one element of B. The set A is known as the domain of the function, the set B is called the codomain of the function. Now, as you saw in Chapter 1 of this course, you can more formally define a function from A to B to be a subset of the Cartesian product A cross B. Remember, A cross B is a set of ordered pairs, an element of A and an element of B in that order. And a function is this subset of this Cartesian product which contains one and only one ordered pair of the form AB for each A belonging to the set A, belonging to the domain. And you also saw rules about being one-to-one and onto. Function is one-to-one if and only if there's at most one pair for each B belonging to B, and onto if there is at least one pair for every element of the codomain B. Now, there are many cases in mathematics where we want a way of connecting or relating elements of two sets A and B without this restriction on elements of the domain, set A, appearing only once. For example, suppose we're considering the non-zero real numbers, we will often want to discuss both possible square roots. There are two square roots for every non-zero real. We can't talk about a function that would take, say, 4 to both 2 and minus 2, it's two square roots, or take minus 9 to both 3i and minus 3i. But clearly, when we're taking square roots of non-zero reals, it's going to relate one real to two, in general, complex numbers. It's not a function, but it's still a relationship, a way of linking the one real to two complex numbers. You've met other examples of the same sort of concept. Subset is an example of a concept where we're going to link one thing to several things, one set to several subsets. You know exactly how many subsets there are if you're finite, of course. You learned that in the previous chapter of the course. We've looked at congruence in this chapter of the course. Congruence in two different senses, congruence between integers. You can talk about more than an integer being congruent to more than one different integer. And similarly for congruence, say, of triangles, of geometric figures. You could draw three congruent triangles, and the first triangle is congruent to two triangles. Not a function, but it's still an obvious relation. Divisibility, yeah, that's another concept of the same sort of thing, where you've not got a function, but you've got something more general. Less than is another example. You give me any number, 5 say, and there are obviously several different numbers, infinitely many in fact, that are less than 5. So we can't map 5 to one number less than it is mapped to infinitely many. And the most important of all these relationships are equality. Equality is the most important relationship of all, and it's not a function, not in general. As these examples make clear, particularly the examples of subset and divisibility, we've still got an order involved in here, right? Particularly less than, that's clearly an order. So in order to capture the idea we want to look at the Cartesian product, because the Cartesian product builds in an order between the sets A and B. So that's what we want to do. We could drop the restriction in the Cartesian product way of looking at functions, and what we get is a thing called a relation. A relation R, typically R is the symbol we use, from A to B is just any subset of the cross product, the Cartesian product A cross B. Again, we call A the domain of R and B the codomain of R. And if AB is in R, in other words, if the ordered pair is in this relation, this subset, then we say that A is related to B by R. And we normally use the same symbol. We would normally write that in this way here. A related to B is how we'd read that. We use the same symbol for the subset as the relation. And in fact, it's quite common to just talk about A being related to B and writing ARB rather than talk about the subset of A cross B. Well, that's always there in the background. If A and B are not related, so if AB is not in the set subset R, then we write A not related to B is how we read that. We just put a cross through the symbol R. And finally, for our definitions, a relation on a set from a set to itself, in other words, a subset of A cross A, is just referred to as a relation on A. Well, let's look at some examples. And the first one is that every function f from A to B is going to give me a relation from A to B. You just take the subset of A cross B given by the ordered pair f and f of A. That's a relation from A to B. Well, what about some examples that are not functions? Congruence. Congruence modulo M is a relation on the set of integers Z. And this is the relationship. It's the set of all ordered pairs AB, where AB are integers. And this ordered pair AB belongs to R if and only if M divides the difference A minus B. In other words, if and only if A and B are congruent modulo M. Now, this is not a function. Take the example where M is 3. then we see that 0 is related to 3 because 0, 3 is in this set, and 0 is related to 6, and it's related to 9, and related to -3, and, well, many, many others. So it's not a function, but it is a relation. It's a relation on Z. It's a subset of Z cross Z, the Cartesian product of Z with itself. Congruence is still an example of a relation defined by a rule, but we can define a relation just by listing the ordered pairs if we want. Here's two sets, A is alpha, beta, gamma, and B is just the set 1, 2. And then I've just picked 4 different elements of the Cartesian product of A and B, alpha 1, alpha 2, beta 1, and gamma 2. That's a relation from A to B. For example, we see that alpha is related to 1, alpha is related to 2 because alpha 1 and alpha 2 ordered pairs in R, but beta is not related to 2 because the ordered pair beta 2 is not in this set R. Now, this last example illustrates something else that's important about relations. Relations do not need to be between two examples of the same type of object. It doesn't need to be between two types of numbers or two triangles or anything like that. We've just seen a relationship between Greek letters and integers. For other examples that are like this, well, let's look at the general geometric relation of lies on. Right? How do you define this? Well, you could say, for example, a point and the line are related if the point lies on the line. And that's between two completely different types of geometric object, a point and the line. Furthermore, when we're talking about A congruent to B mod M, well, it really involves 3 integers. So we could think of congruence more generally as a relationship not between 2 integers, given M, relationship between A and B, they're related if they're congruent mod M, but a relationship between 3 integers. So really, congruence is a subset of Z cross Z cross Z. It's what we refer to as a ternary relation because it involves 3 sets. And clearly you could generalize a ternary relation on Z to a ternary relation between 3 sets or 4 sets or even more. What we've actually been looking at here as a subset of A cross B is really a binary relation, and it's a relationship between 2 sets. Now, as far as we're concerned in this course, we're only going to be looking at binary relations, not the more general cases. So far, we've seen 2 different ways of defining relations. The first way is where we used for a function or congruence. We described the relationship. We gave a rule for how one element is going to be related to another element. But we also did a definition of a relation just by explicitly listing out the ordered pairs that belong to the relation. Now, there are other ways of defining relations, particularly for finite sets. Suppose you've got 2 finite sets A and B with elements little a and little b respectively. You can describe a relation from A to B by, well, one way is to draw what we call an arrow diagram. You draw dots, which we refer to as vertices, labelled with the A's and the B's, and we join them by an arrow if and only if AI is related to BJ. So a vertex labelled AI is joined to a vertex labelled BI by an arrow if and only if AI BJ is in the relationship. In other words, if AI and BJ are related. Another way of doing this is to actually write out a rectangular array of numbers, a matrix, where the entry in the ith row in the jth column is, which we refer to as M sub ij, and Mij is 1 if A, I and Bj are related, otherwise it's 0. Doing this, of course, implies that we put some order on the vertices of A and B so that the ith column corresponds to the ith element of A. Let's look at these 2 ways of representing one of the relations we've met before. Let's look at the second relation in example 23, the one between the set alpha, beta, gamma and the set 1, 2. And there's the relation to remind us. Well, here's our arrow diagram. So we draw vertices, 3 vertices labelled alpha, beta, gamma from A and 2 vertices for B labelled 1 and 2. And we join these up, well, when they're related. Well, we know that alpha is related to 1 and alpha is related to 2, so we draw arrows from alpha to 1 and alpha to 2. Beta is related to 1 and gamma is related to 2, so we draw in 2 more arrows from beta to 1 and from gamma to 2. And that's our arrow diagram way of representing this relation. What would our matrix representation be? Well, let's just stick to the order that we've currently got with our 2 sets A and B. So the rows are ordered for alpha, beta, gamma, and the columns ordered for 1 and 2. In that case, this is the matrix representation. Look at the first row, that's the row corresponding to alpha. We have a 1 in the first row, first column, because the first entry of A is related to the first entry of B, and the first entry of A is also related to the second entry of B, so that's why we've got a 1 in the second column, first row. When we now turn to looking at the second row, well, that's the row corresponding to beta. Well, beta is only related to 1, so the only 1 that there is in the second row of the matrix is the one in the first column that corresponds to beta being related to 1. And there's a 0 in the other entry because beta is not related to 2. And finally, in the third row, well, gamma is related to 2. That's the only thing gamma is related to. So that's why we've got a 1 in the third row, second column, and a 0 in the third row, first column, because gamma is not related to 1. So that matrix there, this matrix, is our matrix representation of the relation given the order of the elements that we talked about earlier. For a relation on a set, as opposed to between two distinct sets, then we don't really need two copies of each element when we draw the arrow diagram. We might as well just have one vertex for each element and just link them in that diagram. What we get then is something called a directed graph, also abbreviated to a digraph. I'll almost always use the term digraph, just because it's less effort to say. Let's look at an example. Let's take the set 1, 2, 3, 4, and let's look at a relation on A given by M and N are related if M divides N. So that's a relation on A, which I'm defining by a rule. Well, if you were to do the arrow diagram the previous way, we'd have two copies of each vertex for every element, what we've got here, and then we'd have to join them up. Well, what about 1? 1 is related to what? Well, 1 is related to an element if it divides an element, but of course 1 divides everything. So in fact we have a relation we have an arrow going from 1 to every element. What about 2? Well, 2 doesn't divide 1, it does divide 2, doesn't divide 3, does divide 4. So 2 will be linked in the arrow diagram to both 2 and 4 and nothing else. What about 3? Well, the only element of 1, 2, 3, 4 that 3 divides is 3 itself. And the only element of 1, 2, 3, 4 that 4 divides is 4 itself. So that would be our arrow diagram in the previous method for this relation. Clearly, it's a bit clumsy. We've got too much information here. If we did it as a digraph instead, what we do is what we've done here. We just have one vertex for each element, and we join in this diagram if we're related. So what about 1? 1's related to everything, so we link 1 to every element. And that will include a loop linking 1 to itself, because 1 divides 1. And we've got a link from 1 to 2, a link from 1 to 4, and a link from 1 to 3, because 1 divides everything. What about 2? Well, we already saw that 2 divides itself, so that's going to put a loop at 2, and it also divides 4, so that's a link from 2 to 4. And as far as 3 or 4 is concerned, the only elements that they are related to are themselves, so that's why we get these loops at the vertex 3 and 4. And this diagram here on the right is an example of what we call a digraph or directed graph. It's a collection of vertices, dots and lines joining them with arrows with directions on them. What would this relation look like as a matrix? Well, here's a relationship again. M divides N on ABC. Well, we're going to have a 4 by 4 matrix here, and again it would be logical to keep the rows and columns in the order 1, 2, 3, 4. So the ith row and the ith column correspond to element I. Well, what do we get when we fill it in? I invite you to pause the video and do it for yourself, see if you can't work out what the matrix is going to be. This in fact is what we get. The first row is all 1s because 1 is related to everything. The second row has a 1 in the 2, 2 and the 2, 4 position because 2 is related to itself and related to 4. And the third and the fourth rows just have a 1 on the diagonal term, that they correspond to the loops in the digraph we saw in the previous slide, because 3 is only related to 3 and 4 is only related to 4. So that's our matrix form of this same relation on A. Let me just point out that the matrix representation of a relation is not unique. It depends on the order you give the rows and the columns of the matrix. And let me finish this video by saying that you will look more closely at graphs in the sense of dots joined by lines in the final part of this course. So that concludes our look at relations in the general sense, binary relations at least. What we're going to do in the next video is look at certain properties that binary relations can have, and then we're going to look at two particularly special and important examples of relations in the last two videos.